Okay, we're trying again. Recorder has started. Gavin and Dean, and anyone else who is absent, which is no one. But anyone who's checking out this later?
I just guessed it's
video later.
because I started like copying.
Don't make me give the same lecture I gave to pre-cal about how listening takes you being quiet. Can't listen while you're talking. There's a life lesson in that. Careful. In relationships, you need to listen. Okay. Our goal is to go ahead and tackle section 9.3 today, relative rates of growth, not in proper intervals. Low Siento, again, for doing that next step. We're going to grade right now 9.1, 9.2. For those of you that aren't with us and are checking in later, groups went ahead and checked in already, narrowing down some questions, but we're going to go grade that even. But big idea for today that we're going to be using is if we are taking two different functions, f and g, who are both positive for, f sufficiently large, this terminology, it's getting so highfalutin. We can say if the limit of f over g is infinity, or if the limit of, as we go to infinity, of g over f is 0, we can actually deduce which one is growing faster and which one is growing slower. Some of you might be like, duh. But at the same point and at the same time, this is what we're going to be applying today for relative relating, not like related rates, but relating as in between two functions, their rates of growth. So not just saying limit is 0, limit is infinity, but seeing an application in that as far as how their growth is changing. Anyway, coming back to that in just a second ago, or just a second, or 2 or 3 or maybe 120, but we're building up to this relative efficiency of sequential and binary search algorithms, which is kind of cool, kind of fun. A little bit of a techie application to what we're doing with limits, but first, let's grade. Section 9.1. Section 9.1. Number 16, A, B, C, D. I'll let you guys check. Ooh, we have a recursive rule. Ooh, we have an explicit rule. Number 22, plugging in. Simplifying and solving, and getting an explicit rule. Which 22 is super interesting because they said 1/4, that's 2 to the negative 2. Man, I can bring that in as long as I separate the negative 1. I have like bases, a base of 2 and a base of 2, and they made it all snazzy looking. Even though this is what you would have thought about with your, ooh dear, is this a geometric sequence? Is this geometric? You guys have the question. I don't up here anymore.
Yeah.
Because the common ratio is negative 2? With an initial term of 16? No, I don't think that's right. Sorry, that is the common ratio. Ew, gross. The common ratio is negative 2. There we go. And they're plugging into the ace of 1 times r to the n minus 1, and they're like, that's a 2 to the negative 2, and that's a 2 with a negative. If I separate the negative 1, which we call the alternator, ooh, that's fun, which we call the alternator, then we have like bases of 2 to the and 2 to the, and we put them together. Anyway, snazzy. Helpful to be able to see and to recognize. Discrete function, look at that. For n equals 1, n equals 2, n equals 3, n equals 4. They made their window 0 by 20 to be able to see those terms of the sequence. Not serious. But then taking the limit, we have a convergent one that not only converges, but converges specifically to 0. Not only converges, but converges to 0. Number 38, same thing. Convergent, converging to 0. Number 40, divergent. Why? It'll never make up its mind. It is not getting close or stabilizing to any one term. It is forever oscillating. And no stabilizing link. Number 44, you could have used squeeze theorem. Check it. Oh my goodness, did we do this exact same one? No, but super, super similar.
We did this.
I think we did over.
No.
We did exactly that.
Oh, okay. I just didn't build it from the end and then go to the 2n. Interesting. That's curious. Why did they build it with over n? Huh. I'm just checking, like they were actually solving for this limit, and yet they divided by n and not 2 to the n. That's curious to me. I think I like what we did in class better. I'm just curious as to why, if there is a proper reason for doing 1 over n instead. That doesn't even match up with what they have. 2 to the n can't be rewritten in terms of n. Huh. Muy interesante. Anyway, we have graph C, we have table A, and then we have E. I think that's a typo. Huh. Anyway, section 9.2, we ready?
Yeah.
You can stop me if you're not. Number 6, 1/4. Number 22. 6, 1/4. Number 20 is 2.
ln of 2.
Huh?
ln of 2.
Oh, Los Santos, I didn't keep going. My bad. It was ln of both sides. No, it wasn't. Oh, 2 is the ratio of the inside term. There we go. And then ln's on the outside decomposition of functions, and so therefore ln of 2. Thank you, Ken. Ln of 2. Number 24. Final solution is 1. Because at the end of the day, we have an ln of a limit of the limit we were trying to find equaling 0, and so therefore e to the both sides, and anything to the 0 power is 1. That was them finishing it there at the end. And remember, that is necessary, right? When we have a function to a function, when we have an in terms of x to a in terms of x, a variable expression to a variable expression. Gotta use our ln. Number 36. 1. Number 36 is 1. Which is also interesting, because staring at that, I'm not so sure I would have figured that out. Not so sure I would have figured that out. Without doing like the math, as far as just eyeballing it. This one's indeterminate because of 0 to the 0, but as we know, we can't deal with an f to a g. We need an f over g. We need a ratio where the top and bottom are both 0 or both infinity in order to be able to do L'Hopital's. And so therefore, they go ahead and play around with our ln business in order to get an expression that they can take the derivative of top and bottom with or of, and we end up with, once again, ln of the limit is 0, so therefore e of both sides is 1. Therefore e of both sides is 1. The reason they had to come towards pi over 2 from below, secant is the reciprocal of cosine, and secant has a vertical asymptote at pi over 2. And so if we were considering the limit of secant, which would bounce off of cosine, bounce off of cosine, bounce off of cosine, here's my 0 and pi and 2 pi, here's my vertical asymptote. If I was coming from both below and above that vertical asymptote of secant, wouldn't I be in some trouble as far as having a dne instead of an infinity? Because if they're disagreeing, that would be a dne. That would not be an infinity. So therefore, they needed this to be a proper infinity over infinity in order to be able to utilize L'Hopital's. So they went ahead and defined this to be coming from below. That way it's not dne, instead the limit truly is infinity. So the limit of the top would be ln of cosine of x. I think still infinity. Wait, cosine goes between 1 and negative 1. Wouldn't work for negative values either. Because ln of 0 doesn't exist and ln of negatives don't exist. Oh, hey, they had to do it for ln of cosine also, because they couldn't include this in an ln since that's 0 and negative values, so they had to have it be below 0 and coming in towards. So we're getting closer and closer and closer to 0, which in an ln means going to infinity. There we go. So we have an infinity over infinity. Interesting. Some of you might have gotten stuck way back there. Some of you just assumed it went with L'Hopital's. So dangerous. So sorry. And then you were able to go ahead and simplify and simplify and simplify. They didn't keep doing L'Hopital's. They said, whatever, that's tangent. That's tangent. Nice. Plug it in. Plug it in. That's a fun one. Number 60 appears to be 0 in letter A. But what did you notice in letter B? Oh, if they truly, I don't know if tricking is the right word, but if they got you. Mathematically, the limit is 1. Ooh. Oh, no. Never mind. I thought they were saying the limit is 1. That's more in like earlier when you're first learning limits. That's not necessarily L'Hopital's. They're trying to warn you that because of the table, the limit truly is 0. But if you tried to do L'Hopital's, you would have gotten a different answer. You would have gotten 1/2, I believe, because cosine of 0 is 1, and then derivative of 2x is 2. So if you just went to L'Hopital's being like, it's the L'Hopital's section, yay, let's go with, they're just trying to warn you, remember, you got to plug into top and bottom, and if they're not both 0, L'Hopital's does not apply.
With the student keep doing that,
Yeah, that's the more dangerous part, right?
that's a part of
Is that it was L'Hopital's, and I just keep doing it until everything goes up. Just kidding, you got to keep going until it's no longer 0 over 0 or infinity over infinity. Good, Lorenza. 64C, 66B, and I think that's it. Okay, guys, I have the book open. I am ready. I am at your disposal. If there's something you want to talk about, ponder, ask questions on, get clarification for. Yeah, Patricia.
For 9.1, number 37,
Okay.
the answer in the back of the book is divergent, but you gave us a rule in our notes.
Ooh.
It's like x to the n.
What was it, number 37?
Yeah.
And the limits, like the bounds, were the same, right? Ooh, I did give you a rule, but be careful. What did the rules say? It goes back to pre-cal, and it goes back to geometric sequences and series, technically, and the convergence and divergence of those. Be careful. Whenever I have an x to the n as I go to infinity, as far as a sequence, not series, it will only be going to 0 if the, what we used to call the common ratio, but now it's just whatever that base is. If it's between 1 and -1, I'm good. I'm golden. It's going to eventually converge. But sadly, in this one, you're over. And so as you raise it to higher and higher powers, it's actually just going to grow or increase without bound. The limit will be infinity, which means divergent. But ironically, something just a little bit different, 0.9, is going to converge. On one side of 1, I have divergent all the time. On the other side of 1, I'm going to have convergent all the time. And remember, this is for negatives as well. So magnitude needs to be less than 1, aka the value of the constant, regardless of sign, needs to be in between 1 and -1 for convergence, or outside. Or technically even equal to 1. If it's equal to 1, it would still be, well, the sequence, if it was equal to 1, would still be, would be convergent, because it'd be 1, 1, 1, 1, 1, 1, 1, it'd be converging to 1. I mean, it is 1. The series, though, would be divergent, but you guys don't know that yet. Good question. Anything else? We're good? Section 9.1 and 9.2? Okay, I don't mind going on to 9.3. Gives us more time. Sorry, guys. I thought we'd have a few more. How many of you guys got at least, I shouldn't put it that way. How many groups got at least one question answered during your time? Oh, so we just didn't have a lot of questions. But good job, those of you that did get questions answered. Nicely done. I was thinking maybe we had them and just got them all answered, but we didn't have many. Okay. If you guys need me, come find me. Otherwise, let's go ahead and go to section 9.3, relative rates of growth. Okay, before we get to relative rates of growth, I have a quick intro that I think is interesting. Once again, there are multiple things in your book that I find are interesting. I mean, in the AB one, there probably were super interesting things as well, except we never really were able to slow down long enough to see them. I feel like if Mr. Graff ever got to the point where he could teach calculus, he would bring a totally different aspect, because he would bring in all the philosophers and all the, like, what was going on historically at this time when this thing was, I wish I knew all that. He's really a history teacher, history major, who's transitioning into a math. teaching career. But anyway, he does super interesting things as far as the historical significance of different things. But anyway, I don't know tons. I did take a history of math course. That was fun. Took a couple philosophy courses, also interesting. But when I do see something that is a bit curious, I do love pointing it out to you guys, and especially our book, because in CalcBC every now and then, either you guys in the past or present have asked good questions that have caused me to go deeper, or we just have a little more time, or there are sections like this one that are kind of random, like relative rates of growth. We never did growing faster or slower specifically last year, or even end behavior models. We never used that terminology. So I have to slow down every now and then. So, to introduce this whole section, that doesn't really involve a lot of new math, just applying stuff that we already know for the most part. And you have L'Hopital's, you're empowered by it technically now according to our textbook, we just covered it. So we can do a lot of limits. Don't worry, limits are still a thing as we go into sequences and series. But anyway, I totally don't mind reading it. I do want us to read it together, but if someone has a good reading voice, I am totally fine being quiet. Anybody want to read it? Brian, go for it. Do you want to popcorn it off to John at some point? Go for it too.
Yeah, it sounds kind of mean. The exponential function e to the x grows so rapidly, and the logarithmic function ln of x grows so slowly that they set standards by which we can judge the growth of other functions. The graphs of e to the x, ln of x, and x suggest how rapidly and slowly e to the x and ln of x, respectively, grow in comparison to x. In fact, all of the functions a to the x, for a is greater than 1, grow faster, eventually, than any power of x, even x to the 1 millionth, and hence faster, eventually, than any polynomial function.
Eventually, that's key. Sorry, keep going.
To get a feeling for how rapidly the values of e to the x grow with increasing x, think of graphing the function on a large blackboard, with the axes scaled in centimeters. At x equals 1 centimeter, the graph is e to the 1 around 3 centimeters above the x-axis. At x equals 6, the graph is e to the 6 around 403 centimeters, or around 4 meters high. It is about to go through the ceiling if it hasn't done so already. At x equals 10 centimeters, the graph is e to the 10 around 22,126 centimeters, or around 220 meters high, higher than most buildings. At x equals 24 centimeters, the graph is more than halfway to the moon, and at x equals 43 centimeters from the origin, the graph is high enough to reach well past the sun's closest stellar neighbor, the red dwarf star Proxima Centauri. E to the 43 is around 4.7 times 10 to the 18 centimeters, equals 4.7 times 10 to the 13 kilometers, is around 1.57 times 10 to the 8 light seconds, and is around 5.0 light years. The distance to Proxima Centauri is 4.2 light years. Yet, with x equals 43 centimeters from the origin, the graph is still less than 2 feet to the right of the y-axis. In contrast, the logarithmic function ln of x grows more slowly as x approaches infinity than any positive power of x, even x to the 1 over 1 million. Because ln of x and e to the x are inverse functions, the calculations above show that with axes scaled in centimeters, you have to go nearly 5 light years out on the x-axis to find where the graph of ln of x is even 43 centimeters high. In fact, all of the functions log base a to the x, a is greater than 1, grow slower eventually than any positive power of x. These comparisons of exponential, polynomial, and logarithmic functions can be made precise by defining what it means for a function f of x to grow faster than another function g of x as x approaches infinity.
So this one isn't specifically historical context, although if you but section 9.2, L'Hopital's, Bernoulli, I think Bernoulli they talk about in the book itself. There's some interesting historical stuff there. But in these ones, it's just sometimes numbers don't really mean much to us, and I thought it was kind of cool just taking a second and being like, oh dang, yeah, that is going high. And what's even crazier is we learned in our special converging sequences that something is even stronger than exponential. faster, growing faster than exponential. And what's that one thing that grows even faster than exponential growth?
Number 2.
Exclamation mark.
Factorial. We're cute. It's okay. Factorial growth is even stronger than exponential, but we'll deal with more of that when we get into sequences and more specifically series. More specifically series. I know. I beat you guys to the punch on that one. It's coming. And you'll realize why I have you keep saying sequences.
Not series.
So factorials are going to be a really important thing, especially towards the end of chapter 9 from the other textbook, which chapter 9 from the other textbook we're actually splitting into 2 parts, with multiple forever quizzes and endeavor quizzes. With multiple endeavor quizzes, fill in the blank mostly, which is kind of nice, not the same old like state the whole card, more like do you know the ideas in the card, like they're printed off, it'll be unique, it'll be different. And a couple like quizzes, half tests along the way to make sure it's like we've done a section, do you know what it is? So we're definitely slowing down. But I enjoyed kind of like the comparison of exactly how different. However, to that end, when you hear people saying about like growing exponentially, does it make sense seeing those numbers that realistically there's not much that will truly forever grow exponentially, right? What's that growth that says, okay, it might be exponential for a time, but come on, let's be realistic. Logistic growth. It kind of just highlights how important that growth is, because it's like, okay, let's be real, right? I mean, you guys all know that with fads and trends and all sorts of like, all right, it's going to taper off eventually. So anyway, just kind of interesting as far as exponential, logarithmic, but that's how our book introduces section 9.3, relative rates of growth. So you don't necessarily need to write down this huge box. And to be honest, we're not going to make any forever cards, endeavor cards, out of any of this stuff per se as far as knowing for the AP exam. However, our main goals, obviously our independent variable increasing without bound, hence going to positive infinities, similar to sequences, not series, as n goes to positive infinity only. Comparing growth rates of numerators with denominators. So you're going to see ratios, but kind of like with L'Hopital's, we're going to be considering the functions separately or as 2 separate entities and just using the limit for our benefit or for our analysis of their growth rates. We're going to be using L'Hopital's when necessary, and then this relative efficiency thing is going to come. So I think for most of us, this little bit down at the bottom kind of makes sense. If you want to make a quick note about it, that might be helpful as far as for homework tonight. But once again, we're looking at the ratio of an F to a G or a G to an F. It doesn't necessarily matter which one we put on top or which one we put on bottom. We just need to know how to interpret the limit that we find. But I think for most of us, we're like, hey, if the limit is infinity, the top must have been stronger is how we would have said it before. But technically with the idea of x approaching infinity, we can say growing faster, which is a bit more precise. Or like this one, if the limit of g of x is 0, okay, fine, so g is growing slower. So remember, it kind of determines, or the statement that we can make, we're kind of looking at the numerator, saying, hey, the numerator is stronger, oh, the numerator is weaker. Oh, I mean, the numerator grows faster than, or the numerator grows slower than. So anyway, it's just interpreting those limits. And then if we have a ratio of a leading coefficient situation, we can say they grow at the same rate. Wait, no. The limit is a number. No, they grow at the same rate. Just as they're growing. You can think of, in some senses, one starts off a little higher than the other, which is why even though you might have a constant of 2 or 10 or 12 or -5 or whatever, even though you might have a constant as the limit answer, we still say they grow at the same rate. That's probably the trickiest out of all of this. As far as the ratio is, it doesn't matter. They are still growing at the same rate because their degrees were tied. So kind of drawing the comparison between the degrees of functions, which technically only works for polynomials. We just kind of keep talking about it with other functions to make it easy. But the strength of functions may be a better way than saying degrees. And then this section's like, why don't we just call it their growth, how they're growing? Instead of using that word magnitude, instead of using that word degree, instead of using things like winning or losing. Just slower or faster. Do we have the main idea? I'm going to go ahead and dual page it just in case a couple of you guys are still looking, because I see a few of you that are still writing stuff down. But let's see where this is going. So to kind of summarize a few things, F grows faster than G means, or I should say to clarify, F grows faster than G means that for large X values, sufficiently large is how they would put it, G is negligible in comparison to F. Now, if I say for large X values, you could be like, well, what's large? Oh, it hasn't happened yet. That's why we use the terminology of sufficiently large. Okay, we'll get large enough, and then eventually, so whatever that eventually is, hey. Whenever you have a limit being 0, well, eventually, for sufficiently large values of X, that top is negligible because of the bottom. Or when the limit is infinity, that top, for sufficiently large values of X, is not being affected by that bottom anymore. There is this idea of transitivity of growth rates. You guys remember things like the associative property, the commutative property, distributive property, etc. This is kind of like a transitive property. If F grows at the same rate as G as X goes to infinity, and G grows at the same rate as H, then F will grow at the same rate as H. We're kind of used to some like more basic properties of math following that type of if A equals B and B equals C, then A equals C. Just saying that kind of works for limits as well. And technically you could show it, you could prove it, because you could go ahead and say, well, if that's true and then this is true, okay, fine, I can go ahead and do F compared to H, which would be that quotient if you're trying to compare. F compared to H, that's what that division shows. Be like, oh, fine, I have F over G and G over H, and then a quick little bloop, bloop, got it. Limit properties, I'm good to go as far as the limit of one times the limit of the other. If each individual one is finite and non-zero, then multiplying them will also be finite and non-zero. So you don't necessarily need to know the proof. Once again, not things to necessarily memorize. Just kind of like, okay, if they're saying these words, this terminology, oh, because some of you, when you read L'Hôpital's or when you were doing that homework, I heard you say, what's the stronger form of L'Hôpital's? Right? But did you look in the book and realize that there's a weaker form of L'Hôpital's? Our form is the stronger form. Our form says, hey, guess what? You can keep doing this and doing this and doing this and doing this. The weaker form says, oh, just once is necessary. But there are some conditions to this. Do you guys know what conditions have to be true to the weaker form of L'Hôpital's? In order for a limit to actually equal the function value, when the derivative at that function value, we probably have to talk about something to do with these guys' continuity and differentiability. Oh, that's right. I have a form of L'Hôpital's I wanted you guys to see. But today we were doing so much, so we'll look at it tomorrow. This is the weaker form. Ah, yeah, go once. Stronger form says, what if it's indeterminate again? Not it as in the limit and what the limit equals, but what if the limit of the top and the limit of the bottom are both 0 or both infinity again? Oh, okay. So what we're learning is the stronger form of L'Hôpital's. Maybe some of you saw it. Maybe some of you didn't, but... Oh, I already have stuff solved? That's no fun. You guys. It is fun? Question. If they ask us to show that one is faster or one is slower, what do we really just need to do, based on what we've seen so far today? Take the limit as x goes to infinity, and who's on top and who's on bottom? It doesn't matter. I just figured I'd stop you. It doesn't matter. Why?
Because you can show one is lower or one
You can show it, yeah, you can show the top is slower or the bottom is faster, and that's the exact same thing, right? But this one says show that E grows faster. Well, if they want E to grow faster, I don't know, maybe I should put E on top. Because then I'm hoping that I get infinity. And if it gets infinity, then I'm good. And I can say, oh yeah, E's faster. But what if I had done it the other way and I put the trying to hide that. Whoops. Don't worry. I'm just doing one example for each. Oh, that's a bummer. But could I have done it the other direction, and could I have put the polynomial on top and the E on bottom? Yes. And what's going to happen if E is faster? Yeah. Doesn't matter. I can see who's faster either way. Question, kiddos, without us actually doing all of the work, how could you show that this limit truly is 0?
The bottom is stronger than
Write a paragraph about how the bottom is stronger. How could you show that it truly is 0?
Well, we're plugging a big number.
L'Hopital's. I have infinity over infinity, don't I?
Oh yeah.
Or I could keep on plugging in larger and larger and larger values and show that, oh hey, it's basically just the e, the other one is negligible. That sounds kind of annoying. I would do L'Hopital's, because you would have, what, 3x squared, and then you would have 6x, and then you would have 6, and 6 over infinity, half is 0. If you needed to show it. How about the next one? Show that ln grows slower. Who do you want to go on top? Ah, did you hear that I changed my wording? I said, who do you want to go on top?
X minus ln of x.
Okay, so x minus ln of x all over ln of x. You're comparing to ln, true? Oh, they're using e's and ln's like the whole intro thing. Okay, I get it. Oof. Now, they already gave you the answer. It's kind of like a t-proof, right? They already gave you the answer. What do you mean? What is this supposed to be if ln grows slower than? What is it? Infinity. So that means the top must be stronger, because ln is growing slower than. So you know it needs to be infinity, but how are you going to show it? Because right now you plug in, you get infinity minus infinity, but a really slow infinity all over a really slow infinity. L'Hopital's. We're just practicing L'Hopital's more in a context. If we're trying to show that x squared grows at the same rate as, have we figured out yet? It really doesn't matter who we put on top or who we put on bottom. It's how we interpret the answer. What should happen? Well, this one's kind of easy. Am I going to let you just do a degree test? Okay, fine. Just be careful. Bless you. Oh, because the ratio is 1, they grow at the same rate. No, because the degrees were tied. Could have been a 2 or a 5 or a 10. Still grows at the same rate. It's not infinity and it's not 0.
So what do you expect us to do for the L'Hopital?
I just said
Focus
you're allowed to do a
on
degree test, the polynomials. But I do expect ones that are not clearly apparent to be solved.
So for like question
Number
like
2.
1 and 5, you have to do a L'Hopital.
Oh, sorry. I was meaning 2 as in the second one. Number 5 for sure. Number 1, I'd probably let you off as long as you just show me. Because you're going to have to set up a quotient and you're going to have to give me the proper answer that shows. So you're still interpreting, even though I'm not making you do the tedious, obviously E is stronger than. How about number 13? Oh, this is interesting. 2 functions, okay, ln of x. They grow at the same rate? Yeah, they're both logs. Makes sense to me. Didn't I tell you there are chapters coming where what makes sense to you is going to be wrong?
Yes.
Okay. So how do we show? Well, actually, do we even know what the answer is going to be?
No.
No, it's just some sort of constant. L'Hopital's. See it? But go find me the constant that it better be. Number 31. Show that the 3 functions grow at the same rate. Do I do f over g over h? Yeah, how about do those 2, and then how about do those 2, and as long as both of those are constants, then wouldn't the ratio of that to that be a constant too? Play around with that transitivity thing. Do we have an idea of what we're doing? Yes. Thanks, Ah! You guys are quieter. Oh man, I kept filling in. Sometimes I save over. Well, it depends on what's on here. Hold on. I don't want to totally give away all the good stuff. Remember that whole efficiency thing is coming. Yeah, no. I do not. Nope. Okay. Bloop. You guys. All right, algorithm efficiency. Algorithms. What uses algorithms these days?
Computers. YouTube.
Everything minus this. And this. And this. Although, maybe I have an algorithm as to what I need here. But, anyway, maybe I'm solving algorithms. Anyway.
It's so fun.
Can't do that.
Algorithm efficiency. The fewer number of steps a computer must take to accomplish a task, the more efficient the algorithm. Why does this make sense? The fewer number of steps it takes you to do a homework assignment, the more efficient you are doing it. True? Don't we all want to do things efficiently? Is efficiency cheating? No. Okay, life lesson. But come back. Efficiency. Why does everyone want an efficient worker? They'll get more done, and they'll hopefully get it done better, because they're not just doing it fast, they're doing it efficiently. It's not about being fast. It's about being efficient, which sometimes means you have to go slowly. Wisdom. Takes time. Trial and error. Usually a lot of mistakes along the way. Being willing to grow and change and adapt depending on what authorities tell you. Or mentors guide you. Or Jesus impresses on your heart. Or, okay. Illustration. Okay. Webster's Dictionary, sequential versus binary search. I don't have this one written out. Do I have it written out on the next page? It'd be nice if I did. If I did, it probably is written on anyway. Hold on. Oh, I don't have it. Okay. Webster's Dictionary. You guys are writing down. You're even peeking at maybe number 43 with search algorithms, trying to figure out which one is the most efficient. The application itself isn't super hard. The application itself is, let's see. Which of the algorithms is likely the most efficient in the long run? This is just building up. This isn't the concept itself. We just want to take a limit, and we're going to have to do a transitive property for this one because we have 3 different ones. Question. Would the more efficient algorithm be the slower growing one or the faster growing one?
Slow.
Why slow?
Because you don't have to do that much of calculation.
Because then you don't have to do as much. So it's not so much with efficiency in algorithms, it's just another application. It's not so much about how it's growing. I want the growing fast one. No, because that means there's more to it. And if there's more to it, remember the fewer number of steps. So I actually want, in a sense, the weaker function. Because I want the fewer number of steps accomplishing a task instead of some nasty program that's like being totally bogged down because it's doing the same task but in a less efficient way. Okay, Webster's Dictionary. I'm not sure if I'll have time to get this one done. I should have had it open. Here we go. Webster's Third New International Dictionary lists about 26,000 words that begin with the letter A. I'm just in the A section. Good? 26,000 words. Okay. One way to look up a word, or to have a computer look up a word, is, or learn if it's not there, is to read through the list one word at a time. First, second, third, fourth, fifth, sixth, match it, try to match it, try to match it, try to match it. Until you either find the word or determine it's not there. This sequential search, going sequentially, first, second, third, all the way to the 26,000 method, makes no particular use of the word's alphabetical arrangement. You are sure to get an answer, but it might take 26,000 steps. Because imagine if it's not there. It's going to go through all 26,000 words, right? Another way to find the word or to learn that it's not there is to go straight to the middle of the list. But wait a minute, what if it's like absolution? Isn't that right near the beginning? You would find it real fast. Yeah, but what if it's axe murderer? Right?
Or
I couldn't think of anything else that goes in the A and something real close to the end. That's Aslan. Okay, we could have done this. Okay, so I was like Aslan and then Aslan said it. I was like, okay. Stop. Why would we go to the middle? Couldn't you check the middle word and see the A and then the next letter and see if this one's higher or lower than? Right? Because if you've numbered A through Z, that's 26, and you could go to like AM and be like, oh, hey, I'm looking up AC, that's earlier. You can numerically state a word, right? So then you can go halfway, give or take a few words. If you do not find the word, if that's not it, then go to the middle of that half. And then go to the middle of that half, the appropriate one where it is. And then go to the middle, go to the middle, go to the middle, go to the middle. Yeah? The first way, you could have taken up to 26,000 steps. But the binary search method eliminates roughly 13,000 words in this first step because you only have to look at half as many. If you do not find a word on the second try, then jump to the middle of that half, etc., etc. Continue this way until you've found the word or divided the list in half so many times there are no words left. How many times do you have to divide the list to find the word or learn that it's not there? At most, 15.
Wow.
26,000 or 15? Which way would you want bogging down your phone? Oh wait, I mean app developers, programmers, efficiency? Anyway, at most 15 because 26,000 divided by 2 to the 15th is less than 1. This certainly beats a possible 26,000 steps. So for a list of length n, a sequential search algorithm takes on the order of n steps to find a word or determine that it is not in the list. If you were to solve to fill in that blank, we could say for a list of n items, the binary search is at most,
Log 2n.
I think it's, is it log 2n or is it n ln n?
Log 2n.
Log 2n. Because we're talking about repeated. Remember that logarithms are exponents? I always lose my remote. Log 2n. Here he is. Thank you. My teachers need pockets. Ooh, or fanny packs, Mr. Grapp. Shout out. Okay. Bloop. We could go ahead and like set that equal to y. We could take 2 to the power of both sides, and we can realize we're talking about like 2 to the power of and how that compares to the list of n items. But anyway, long story short. This was just an illustration. It's not something for you to memorize, but it's still that idea of efficiency. Efficiency, battery efficiency. I've heard that's the new up and coming, like what all the tech companies are trying to battle for because there's only so much more they can do to make their things look cool. Now it's all about making it last longer or have foldable screens. Anyway, we would need to do a transitive property, right? We would need to work through the transitive property of basically this comparison for faster and slower. And remember, we are looking for the slowest because we're looking for the fewest number of steps to make it the most efficient as far as algorithms and as far as maybe possibly being a contributing member of society. Bye guys. I'll leave it the work.
I know you.
Have fun with limits. And that's 9 then.